Saxon Algebra 2, Lesson A. Welcome, Cullen, to your very first lesson. We're going to get started and we're going to have fun. I say that with conviction. First, before we jump in, I want to introduce you to the way the lessons are laid out and what my expectations are of you while I'm teaching. If you look in the book, and that's going to make quite a harsh shadow. Let me move my light just a bit. Okay. In this book, there's a lesson A and a lesson B that are kind of review lessons to kick us off. That's kind of nice of John to kind of set them aside as special review lessons, but it's kind of a pain because they're really long lessons. Look at all those. There's 1, 2, 3, 4 major topics. And when you flip through, which you don't need your book, you don't need to do that. There are more than the usual number of terms and items to discuss. That's because we're at the very beginning and we're doing what for most students is a lot of review. I think it's going to be review for you too. So what we're going to do is we're going to cover just these first 2 topics in this video, and then you and I will talk and see how that much is sitting before we go on to the 3rd and the 4th topics, okay? So this is kind of like half the first lesson, but it'll still be plenty, don't worry. I'm gonna give you lots of information. What I would like you to do while I'm talking away in this video, which by the way, I don't like, it's much more interesting if we can sit together and have an exchange. And we will do that once COVID is on a leash. But what I'd like you to do now is grab a paper and anything to write with. And I want you to copy along and take notes while I'm talking to you. The main reason I want you to do that, Cullen, is simply to keep yourself from being bored. Most of us learn better if we're physically moving in some way. To just sit perfectly still is very counter to the way our biology and our brains were designed to learn, right? You didn't learn how to hunt a woolly mammoth by sitting in a classroom and having the key hunters in your community draw a diagram of a woolly mammoth on the board while you sat and watched. No, you would grab your arrows or whatever and follow, and you'd go out and you'd learn in the field, right? Well, math doesn't lend itself in quite the same way, so we have to improvise. And the best way I can improvise a woolly mammoth hunt is to say, just write down what I'm writing down. Don't worry about it being perfect or exact. If you want to know what I said, you can always play this video over again. But just writing will keep your mind engaged. It'll keep your body moving. It helps your brain absorb the information a little more effectively than just sitting perfectly still. So, right, and I don't care. You can do it in a notebook. You can do it on the back of your grocery list. You can do it with a crayon. It doesn't matter to me because, again, we're not trying to create a beautiful permanent record. We're just trying to keep your brain engaged in the process. So pause me, go get something to write with, come back when you're done. All right, I'm assuming you're back. So what I'm gonna do is I'm gonna carry on. The front part of each lesson is narrative and examples. That's my job, is to go through that with you and for you and teach it to you. So I'd say about 70% of the time, I teach the material just the way it's presented in the book. The other 30% of the time, I've come up with better ways that I prefer to introduce it. And so I do not promise you that my lectures will always match to what's in the book. Sometimes they'll be better. Don't tell John, okay? All right, so let's start in with our geometry review. And again, just copy down whatever I write down. If I start going too fast, which I know I will do because I get really excited about this because I think it's really fun. So pause me if I'm going too fast. All right, feel free. That's what that's one of the major advantages of this format is you can pause me. Okay, here's the thing about mathematical terms and geometric terms in general. Some of the most basic ideas are fairly what I would call vague or undefinable. We take our best shot to define those, but then we use these terms to build more specific and precise terms. So in the beginning, sometimes this stuff sounds a little hazy and weird, but once we get those ideas settled, then we can be more precise. And that's exactly what we're going to do today. We're going to start with the basic element of geometry, and that is the point. That is a point. A point is a location in space. Now, technically, a mathematical point is almost a scientific idea because it's tiny. It's like a little atom or an electron. It's like a tiny, indefinably small, there comes the vague, indefinable part, precise little location in time, and let it bend your mind a little bit that it's way smaller than this. It's many. But if we take a bunch of those tiny little infinite points and line them up perfectly, pretend it's perfect, and if we put them so close together that they are unbroken, then that creates a line. Make sense? So a line is a collection of points. And the cool thing about a line is that it goes to infinity and beyond. Okay? So a line is infinite. Now what happens if we take a line, a series of points, of locations, and we nudge it a little bit? So it's not so perfectly straight anymore. Now we've created what we call a curve. All right? So these ideas are fairly vague and undefinable, but once we get that going, we can get more specific now. So over here on the more precise side, I'm going to say for any 2 points, I'll make them a little bigger so you can see them, there's only one line that goes through them, right? Any 2 points determine one specific line. I'm going to write that down. And then I'm going to tell you why I hate to write out mathematical things in words. All right, that's the sentence. I'll give you a second to finish writing it. Words are almost incapable of succinctly describing mathematical ideas. It takes a lot of words to do what a picture or a set of numbers and symbols can do quite quickly. Once you know what this means, you can look at this and go, oh yeah, there's the 2 points, there's the line, there's no other line that could connect those two. I get it. These words are almost dangerous because they almost add confusion to it. So whenever, I try not to use a lot of words in my lectures because pictures and numbers do a better job. All right, this picture also introduces the idea, I'm going to redraw it again here, that sometimes we don't want to talk about the whole infinite line. We want to talk about just a special chunk of it. So what we do is we put the points in and we give them names with letters, and then we talk about what's called a segment. A segment is just a manageable section of the line that has a finite beginning and end. Sometimes we call it a line segment. I usually just say a segment, same difference. But we can note that if we want to write about it. Sometimes we just write AB, but sometimes you'll see, that's my favorite one, is just to put a straight line over it, or sometimes people will make it super fancy and put the line with little dots. So all of these notations are referring to this little chunk of line. All right? Yes. You can also change the order of the letters. So we could write it like this, right? Gee, I don't know why people think math is confusing. I mean, here's this little chunk of line and we thought of 6 different ways to describe it with letters and symbols. That's confusing. I almost always am gonna choose that presentation, all right? So I try to keep it as easy as possible. And for what it's worth, John does too. All right. And then we can also talk about the length of these, and we're going to get involved in some problems later on where John will give us the length of these segments and we'll do little calculations with them. All right. Now, then there's also the idea of a plane. And a plane I kind of put over on this side where it's a little bit vaguer. These were pretty specific, right? And we're going to add more to the specific. We're almost done with the vague. The plane is, it is a flat surface, like a piece of paper, except a piece of paper has a thickness. It's not a very big thickness, but it does have a thickness. And a piece of paper has boundaries, right? It's only so tall and only so wide. A plane has no boundaries, so it's infinite. And it has, this is a little head bindy, it has no thickness. And again, that's kind of like the idea of a point where it's like microscopic. It's a theoretical idea. So when we are talking about, say, parallel lines, which you probably know what the word parallel means. They're two lines that run next to each other and never touch. They never get any closer or farther apart. Obviously, my lines are not precisely parallel because I'm not perfect. But the idea is that they are on the same plane. And they are literally on the piece of paper, aren't they? We don't have a line coming out of the paper and then going down through my table, do we? That would not be in the same plane as these lines. So when we're talking about lines, we're usually talking about being on the same plane, okay? That's all I want to say about that. And planes, okay? I always just think of a plane as a piece of paper, and that helps me visualize it. Okay, that's our geometry review. We started with the very basic element. We have not seen any numbers yet, just letters and symbols, but we're wrapping our heads around some ideas that we're going to build on very soon. All right, I need to swap out my marker because that purple one has just about had it. Luckily, I have more. Okay. Now let's talk a little bit more about angles. Okay. An angle, let me introduce one more idea that will help us understand angles. Here's our line, right? And we talked about how we can identify segments, but we can also identify, this part is the segment, right? Between the two dots, the 2 points. But if we have a point on one end and then an infinity arrow on the other, we call that a ray, right? So if I want to draw just a ray by itself, it looks like that. And the symbol for that, let's just put in some letters. Let's do A, B, C. I could call this ray B, C, and then the picture, the symbol is typically done like that, all right? So we put the letters in the same order that they are in the picture. I can put them here too, if that helps. And then we draw the little arrow in the direction that the arrow is actually in the shape itself. All right, so an angle can be thought of as two rays with the same endpoint. And again, those words, most students hear that and say, what? And sometimes I even listen to the words coming out and go, oh, that sounds so much harder than it is. Look, here's the point. Here's one ray, here's another ray. That's an angle, yay. Okay, now we group, so an angle is very specific. We're really not gonna talk about these vague, undefinable terms anymore. We've waded through all of those and we're now ready to talk about specifics, so I'm happy. So an angle is two rays with the same endpoint and it makes this classic shape. Now, we can categorize different kinds of angles, and you've probably seen this before. The biggest and best, in my opinion, is what we call a right angle. A right angle sides make a perfect square. Perpendicular is a word that we use to describe that. This little box tells us that it's a right angle. These guys intersect each other in a perfect square, and we're going to talk about how to measure that angle in a few minutes. But right now, I just want you to remember that right angle is that perfect square. Then we have what we call, it's like this one. We have an angle that's smaller than a right angle, and we call those acute angles, right? If we visualize what a right angle would look like, an acute angle is smaller than a right angle, right? And then we can have something like this bad boy. And again, if we imagine what a right angle would look like, we can see that this angle is bigger than a right angle, and we call this obtuse. All right? And then another version, you say, wait, you're drawing a straight line. I thought it was an angle. It is an angle. It's an angle that goes all the way from one side to the other, and we call that a straight angle. Fancy name for a line, right? This is an obtuse angle. I'm just going to add angle to all of these. Now, how do we measure angles? Because we do. We start, the easiest thing to remember is that a right angle has 90 degrees, right? The degree is the unit of measurement for measuring angles and circles. We'll get to those. So a right angle is equal to 90 degrees. An acute angle is any angle that is less than 90 degrees, right? We drew our picture here to show how that's where the right angle would be, but ours is less than that. And you guessed it, an obtuse angle is greater than 90 degrees, okay? And a straight angle, if you can imagine the right angle here, we could draw it like that. So this would be 90, and this would be 90. So a straight angle equals 180 degrees. Two of them put together. A right angle equals 90 degrees. I'll put that too. All right? So hopefully this is ringing a few bells in your brain, but these numbers we're going to see give us some tools to play with some really simple and fun problems. All right. What else do I want to tell you? Oh, I want to tell you about a circle. How many degrees are in a circle? Well, you may already know, since you did not fall off the turnip truck yesterday, but here's a really easy way to remember it. If we think of our circle as 4 right angles put together, right? And we remember that there are 90 degrees in each right angle, then that helps us remember that the full measure of a circle is always 360 degrees. Good to know. I bet you knew. All right, few other tidbits. That are a little bit less critical. The stuff that I've been telling you, we're going to use that in just a minute. Normally when we draw an angle, we think of it as we start here and we measure back to the top piece. When we get to trig, this is always the way that we'll measure. We start on what is the horizon line and we measure counterclockwise. We often call this the initial position of the angle because it's kind of the starting place. And then we call this one the terminal because it's where we stop measuring the angle, all right? And so we might measure this and this might be 50 degrees, okay? But we can also measure angles, and again, we'll get into this in trig, where we start here at the initial, but we go past the terminal and come around all the way again. How big would that angle be? This one is 50, just this much. Well, we can say here's a full circle, so that's 360, plus there's that 50 again, right? We're measuring it further out, but it's the same thing. So this angle could be 360 plus 50, which equals 410. So angles can get kind of kooky if we start measuring around and around. We're not going to do that anytime soon, so don't worry about it. But I just want to kind of drop that in. And then the other thing I want to tell you is that we sometimes refer, if this is the main angle that we're talking about, we can measure the other part of the circle, right? And we sometimes call this the reflex angle. I don't usually use that term because most students don't know what they don't remember this term. I'll usually say something like the outside of the angle or the other part of the angle. So don't worry so much about these ideas. I want to just put them in the back of your head and they will live back there until we need them, which really won't be until trig, which is several lessons in. No, several dozen lessons in. All right? Now, let's go back to something really practical and useful. Here's a right angle, and I'm just going to divide it arbitrarily. I'm not measuring these. I'm just going to draw a line to divide it, okay? This one I'm going to call angle A, and this one I'm going to call angle B. I don't know, but I can say this too. It's a right angle, okay? I don't know how big A and B are, but I can say one thing for sure. Angle A plus angle B have to add up to 90 degrees, right? Because the two of them form this right angle. So I don't know what either one of them is. If I knew A or B, I could figure out the other one, right? Because if A, say A was 30, then I know, well, if the total's 90 and this much is 30, then this much has to be 60, right? I can use some simple math to deduce that. But I know for sure that they have to add up to 90. We call these complementary angles because they add up to 90. Similarly, this time I'm going to draw a straight angle, and I'm going to do the same thing. I'm just going to randomly divide it. I'm not measuring that in any way, but I'm going to call this angle C and this angle D. And what we know is that C plus D have to equal 180 degrees because they form a straight angle, right? And we just said back over here that straight angles are equal to 180. So that tells me I know that C and D add up to 180. So again, that doesn't help me with numbers, but if you told me how much C was, I could figure out D. And if you told me how much D was, I could back into C just by using subtraction. This pattern is called supplementary. I cannot really tell you why these words were chosen to describe this pattern of 90 degrees or 180 degrees. And everybody gets confused. Which ones are complementary and which ones are supplementary? Here's how I remember. 90 and 80, put the numbers in order. C and S, put the names in alphabetical order. So C comes first, so it goes with the lower number. S is later in the alphabet, so it goes with the bigger number. This fact we're going to use a lot, and we're going to do it pretty much right now. Oh, there's one more tidbit I want to show you. Maybe two. Don't hold me to it. Once I get going, I just want to tell you all about this stuff. All right, this is a pattern called vertical angles. Okay, they basically make an X. And here's the cool thing about it. Vertical angles always create a pair of matching angles. So this angle and this angle will be the same. And this angle and this angle will be the same. That is very useful information in the problems that we're going to do. So vertical angles create two pairs of identical angles. And by identical, I mean, yeah, they look the same, but they also measure exactly the same amount. Very useful in problems. One other, this is just notation that I want to tell you. Sometimes when we're talking about angles, we might say angle A equals angle B. Or sometimes people will use this notation. The measure of angle A equals the measure of angle B. So these two notations mean the same thing, all right? And John mixes it up. He uses different patterns. All right. Woo! We just covered a lot of ground, didn't we? Now we're ready to put this into practice, and I'm going to show you 3 problems that that John has created for us just based on what we've learned here. So here is the first one. It's example 8.1. John tells us to find x and y, and then he draws a picture for us. And I'm going to copy the picture into my book. Here is a pearl of wisdom for you, Cullen. Whenever John draws a picture, I mean, there it is, right? Like, I'll just show you. Here it is, right in the book. It looks complicated, doesn't it? Don't worry, it's going to be fine. It's fine to look at this picture and try to do the work here, but I don't recommend it. What I recommend is that you take a few extra moments to draw it out on your page. And I'll tell you why. When you draw it, you notice things that you don't notice if you just glance at it, okay? I find this true of myself, and I've done these problems dozens of times. You just notice things differently when you actually draw them out, and it will help you find the solution to the problem, all right? So I see this. My eye goes toward the top of the problem first, and I see that there's a line like this, and then this. Now that line always tells you that we're talking about the angle, and right by it, it says x degrees. Okay, so that's a mystery. We don't know how many degrees that is. Over here, there's another one of those lines, so that's talking about the size of the angle again, and it says 30 degrees. Oh, I'm gonna keep drawing the picture, but as soon as I do that, I notice something. These guys are in this right angle together, so I know they have to add up to 90, and I know one of them. Ooh, I know how to do that, right? So I get excited. I think, okay, I'm gonna keep drawing, but I can go back to that. Now, here on the bottom half, there's a line that goes kind of like that, and then it's similar. Here it says this angle, and it says y degrees, unhelpful. And then over here, it says 40 degrees. Okay, that's the whole picture, and John's instructions tell us to find x and y. If you need a hint, it almost always helps to work in alphabetical order. So you don't have to do it necessarily in that order, but I always give that to students as a tip. Take them in alphabetical order unless you really see a fun reason not to. So I'm gonna go back to our x here and go, okay, I get it. Here's the 90 degrees, which I know because of this. If this side is 90 degrees, and that's clearly a straight line, then this has to be 90 degrees too. So I can add that into my picture. These guys fit together. They add up to 90 degrees, and I know one of the angles, so that means that x must be equal to 90, the whole thing, minus the 30. And that tells me that x equals 60 degrees. All right? When you are doing your homework, which you will be doing soon, show all your work. As you know, because you are a professional working in the real world, there's Gracie speaking. Other people always want to look at our calculations. Math is rarely something that we do all by ourselves and no one looks at. So people always want to see, how did you come up with that? So it's very important that we document neatly and carefully so that other people can follow our train of thought. This is how I do it in this problem, all right? What I want you to do is copy the way I do it, because I use the classic style and I'm very particular about the way I document. So I want you to copy that and it'll become second nature to you and you'll do it the same way. Always box your answer, and then the way that I have you do homework is I always have you check the answer immediately, because there's no point in doing a math problem if you don't know if you got it right or wrong. So immediately I will teach you how to do that. You're gonna check your answer. I check my answer too in the book, and I always put a smiley face. You can put whatever you want, a star, a smiley face, a check mark. I had one student who was a middle schooler who decided he was gonna draw water balloons. And every single problem for every single lesson that year, he drew a water balloon by every single answer. He was very committed to it. So do whatever you like. All right, so we determined those were complementary. Yes, complementary angles. We did the math and we found out that x equals 60 degrees. That's correct. And we see, oh, John's done a very similar thing down here, except that they are supplementary angles. So y is going to be equal to 180, the whole thing, the straight angle, minus this 40. So that tells us that y is equal to 140 degrees. I put that in a nice little box. I remind myself, oh yeah, that's supplementary, right? Complementary, supplementary. Those words were never used in this conversation, but we know that they're there. Okay, so that's the first example. That's the first kind of problem you'll be working in this lesson. I flip. I check to make sure I'm still lined up. My phone has snuck over. There. All right, let's try the second one. Example A2. Find x, y, and p. That's kind of random, isn't it? Okay, so I see this. Soon as I draw that, I think, oh, vertical angles. We talked about those, didn't we? They create two pairs, okay? So as I'm drawing the diagram, I'm just thinking about the shapes that I'm doing, and I'm starting to play with the ideas in my head. How might these facts that we know relate to this picture? All right, now I've got some information to put in here. X degrees, Y degrees, 50 degrees, and P degrees. All right? Now, I told you that alphabetical sometimes works. Here's a great example of when it doesn't work. P is the first letter, but this doesn't give me anything, right? They're opposites. I mean, they're opposite each other, so I know they're the same, but I have no idea. So here's another hint that I'll give you. When my first hint doesn't work, go to where the numbers are, okay? And figure out what can you do with that number. 50 degrees, okay, this is his partner, right? This is the partner to the 50-degree angle. So that tells me that x must be equal to 50 degrees. And that is correct. All right, but that doesn't tell me anything about y and p. So that's kind of a bummer. So I'm gonna sit and think about that until I realize, look, if you think of this as the straight angle, and that is the line that divides it into two, then we know that these two guys are supplementary, right? There's the flat line, there's the divider line. And I already said that this one, sometimes it helps to do this too, to write your numbers into your diagram. I already figured out that that is 50, so y has to be equal to 180 minus 50, right? Because if they're supplementary, that means they add up to 180, and so y must be equal to 130 degrees. All right. I feel good about that. And also we're correct. But what about P? We still have to find P. Now there's two ways you can logic out P, and I bet you have started to see them by now. One way we could do it is to say, okay, well, if that was one set of supplementary angles, then we can go like this, and these two guys also have to be supplementary. So P would be equal to 180 minus 50, which would be 130. That works. Or the other way we could get to the very same answer is to say Y and P are vertical angles. So they have to be the same. Either way we slice it, we're going to get that P also equals 130 degrees, right? It's a supplement to 50, and it's vertical to Y, which we determined was 130 also. All right, double checking our answer. Yay, 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 got it right. So again, I box my answer. Now, I take extra pains to make my work super white spaced and big because my students need to see it when I'm filming. But one of the biggest challenges I have with my students is getting them to use up enough space. A lot of students want to write really tiny and small and squeeze everything in and use up every square centimeter of the paper. Please don't. Give your calculations room to breathe. It makes it a lot easier for you, and it makes it a lot easier for anyone else who is looking over them. Okay, one more. Example A3, and it's a picture that looks like this. Once again, we have vertical angles. Okay, that's cool. We now know that sometimes they make supplements, right? Like we did there. They have the pairs of opposite angles. We know that they're pretty solvable. John tells us to find X, Y, and P again, and then here's what he gives us. P's over here this time. This is 110 degrees. This, okay, now this looks confusing. This says 2y and it's in parentheses. Okay, I'll talk about that in a minute. And then down here is something that looks similarly weird. 5x. Okay? Now, what's going on with these parentheses? What's happening here is that John's trying to say that the measure of this angle is 2y. He puts the parentheses around it because if he just wrote it like this, if he just wrote 2y degrees, then the degrees would really only relate to the y part. But he wants to say 2y is the name of the whole angle, not just y. So he has to put parentheses around it to say that this degree sign relates to the 2 as well as the y. Same thing down here. It makes a simple idea look way more complicated. Don't let it freak you out. Okay, now, how are we going to approach this? We can start just like we did over here. This time it works to go alphabetical. We see here's a straight line. We see here's the line dividing that straight line into two supplemental angles. We know that P and 180 we know that P and 110 have to add up to 180. So we know that P is equal to 180 minus the 110. So P is equal to 70 degrees. Double checking. That's correct, okay? Now, notice that I didn't write, my presentation here has varied a little bit, right? I didn't write equals 70. I could have, but it was starting to get messy to me. So there's flexibility in this to set the problems out the way it looks logical and nice to you. Don't hesitate to use that. Okay, so now we know that this is equal to 70. Okay, now I want to solve for x. Okay, well this is 5x and this is 110. So what that means is that this angle of 5x has to be equal to 110 because they're opposites, right? Vertical angles tell us that they're opposites. Now we have our first little equation to solve. And so I'm going to walk you through this. I know you've spent a lot of time doing this, but I want to refresh you as if you'd never learned it before. Whenever we have an equation, which means there's an equal sign in it, right there, that means we're trying to solve for x or whatever letter we're using for it. We can use any letter we want. X is just the classic one. And so the first thing we do is we look and see where's our x and what's happening to him. There he is, he's right there. He is being multiplied by 5, right? That's what it means when we write a number right next to a letter. It means they're being multiplied together. So in order to get x by himself, we want to do the opposite of whatever is happening now. So if we're multiplying by 5, that means we need to divide by 5. That will isolate our x the way we want. However, one of the major rules to algebra is that if you multiply or divide one side of the equation, you have to do the same thing to the other side. Make sense? You remember, it's all coming back. I know, it's like riding a bike. So these 5s cancel, right? Because 5 over 5 is equal to 1. And 1 times any number, the 1 can be ignored. So we can just eliminate that. And now all we have to do is figure out how many times 5 goes into 110. I'm going to do just a little snippet of long division to refresh you on that. How many times does 5 go into 1? It doesn't. How many times does 5 go into 11? Twice. 5 times 2 is actually 10. We subtract, we get the 1, and then we bring down the next digit. And we see, oh, look, it's going to be the same thing again, right? 2 times 5 is 10, and now we're done, right? That zeroes out. Remember, so our answer is that x equals 22. Okay? Now, just a quick reminder, that doesn't mean this, we're saying this is 22 degrees. We're saying this angle is 5 times 22. 5 times 22 is 110, so that means they're equal. So what we have done is we found an algebraic answer to a geometric question. And these are my favorite kind of geometry problems where we start with geometry and then we morph it into an algebra problem, because I think that's fun. Okay, and one more, I'm going to work it up here because I don't want to turn the page. We still have to resolve the issue of y. And I see, okay, let's do the vertical angle thing again. We could go supplemental, that would work. But let's go vertical angle and we'll solve it this same way. I'll write it up here. 70 equals 2y. Okay? It's an equation, so we know we're solving for a letter. This time it's y. Where is our y? There he is. What's happening to him? He's being multiplied by 2. The opposite of multiplying is dividing, right? Addition and subtraction go together, and multiplying and dividing go together. So when we're multiplying and we want to undo it, we just divide both sides. 2 over 2 is the same as 1, and we can just wipe it out. 70 divided by 2. Remember, this line says, this is the trick to understanding fractions. This fraction bar, if you will, says divided by. Okay, so 70 divided by 2 is our answer. I bet you can do that in your head, and we get y equals 35. Remember, again, just like before, 35 is not the measure of this angle, so we don't put degrees by it. 35 is just the algebraic value for y. The actual measure of the angle is 2 times 35, 70, and that looks right to us. Okay, that is the hardest of the problems that I want you to tackle. So let me show you exactly what I want you to do. I want you to get a nice fresh sheet of paper, either at the front of a spiral notebook or loose leaf is fine too, or a composition book, whatever makes you happy. And let me move this just a little bit. And I want you to turn to page 7. And what I want you to do is look at these first 6 problems. Okay? We are not going to tackle any of these yet, just the first 6. All right? They are very similar to what we just did. Okay? Notice that this one looks kind of weird, but it's a vertical angle. Okay? It looks almost like a plus sign, but we don't have a little right angle marker, so we don't assume it. We just assume, oh yeah, that's vertical angles. This looks a little more natural to us when the X is kind of in front of us, but if you just kind of spin that in your imagination, you can see, well, that's the same thing, right? So you're going to solve for some letters, just as we did. That last one we did is a lot like this one, where we have letters and numbers in some of the corners. This is like the middle one we did. And then here's a couple questions. The supplement of an angle is 40 degrees. What is the angle? The complement of an angle is 40 degrees. So you have to remember, okay, if two angles are supplemental, what do they add up to? And then if one is 40, how much is the other? And then same for the complements. What is the total that two complements add up to? And if one is 40, then what is the other? What I want you to do, Cullen, is I want you to do these problems. I want you to check your answers after you do each problem. Now, some of the answers are in the back of this book. I will show you. Here they are. Notice there's problem set A. Notice that they're only the odd numbered problems. Okay? Once we get into this a little bit, you'll only be doing the odd numbered problems, and the answers are right here. However, it's just the answer. It doesn't give you any information about how John got it, and there are no even numbered problems. That is where, excuse me, I just have to shuffle for a second. That is where this little gem comes in. This is the solutions manual, okay? This one, I don't think it's delivered to you yet because I get the notifications. But what I'll do is I'll send you a picture of this page so that you have the answers to these first problems. Let me move my light so you can see better. So here we have problem set A. You're doing problems 1 through 6. Here are the answers. The answers are in bold, but you also get a little bit of a step-by-step, which is super helpful because what I want you to do is work a problem, immediately check your answer, and if it's wrong, figure out what you did wrong and fix it, okay? So your homework isn't done until it's 100% correct. And you don't wait till the end to correct it because then you've forgotten why you did what you did. It's no good to correct it in the end. The only way to do math problems that you can actually learn from them is to correct as you go. So I'm a huge stickler on this. Now, what does it mean that I put solutions manuals into the hands of my students? It means I really trust them to do the right thing. It also means, between you and me, that I have other ways that I can check to make sure that they're actually learning. So I trust them, but I also verify. Let's just say that. Ronald Reagan, trust but verify. So I will send you a picture of this because I don't know if you have this book yet, but this book is going to become your best friend. And what you're actually doing when you look at the solution and try to figure out what you did wrong is you're teaching yourself. And that's far more powerful than sitting and listening to me talk. When you can actually use this information to help you unravel mistakes that you have made, man, Cullen, that's where the power is. That's where it really gets unlocked. So as much as we all would prefer to just get problems right the first time and zip through our homework, the making mistakes and finding out how to correct them, that is where the most powerful learning goes on. So your homework is vitally important. And me teaching you the lessons, that's just the tip of the iceberg. This is where the real learning happens. So I want you to, and I'm going to talk a lot about how you can embrace this process, how you can be kind to your brain to maximize the strength of this process. And basically, in a nutshell, which I will expand upon as we go, all the things that my generation and generations before thought were important, like sit up straight, have good light, work at your desk, set a standard time every day to do your homework, don't, sit in a quiet space and don't let anyone interrupt you. All of those things that we have always called good study habits, they're all wrong. They're all wrong. The latest research by educators who are figuring out how the brain learns have determined that's not true at all. Novelty is helpful. Motion is helpful. People being around can be very helpful. The way I think of it is the most natural way to learn is our caveman out with his buddies, learning how to throw spears at the woolly mammoth. That's how our brains were designed to learn. So anything you can do that feels good to you when you're learning, throw those old study rules out and do what makes sense to you. Sprawl across your bed. Go sit out at a picnic table. Listen to the guys in the next room arguing while you do your work. Whatever feels comfortable to your brain, do it. And I encourage you to experiment with different settings for your homework and see what works best for you. Okay, so what you're gonna do when you're done listening to this very long-winded video, you're gonna work the first 6 problems, stop at number 7. Then I want you to message me and tell me how it went. If you get into the middle of this and you're hopelessly lost, you can stop and message me right away. But I think you can handle this. I have great faith in you. And then stop, though, at the end of 6 and let me know how it went. And then we'll take it from there, okay? If you have any questions, don't hesitate to call. I am here for you. Good luck. I will talk to you soon.